Okay, here we have a confidence interval problem for a paired sample, and then we have a follow-on question to that about a hypothesis test for a paired sample, so we'll do both of these here. And in this case, we've got a 90% confidence interval that they want us to calculate for a paired sample. So remember, a paired sample, like we talked about in class, is if you're comparing two items, you know, the results from two, but there's a possible biasing factor or something that will influence the outcome. The example we used in class was if you're comparing the paint coverage for types of paint. If you've got 2 gallons of paint or 2 types of paint, you want to make sure that the people applying the paint are equally skilled or unskilled, as the case may be. And so you would pair them up, and so you would have the same painter or group of painters use 1 gallon of paint and then the other, and so on, and pair these up so that you eliminate or account for the influence that might have on your outcome. Okay, and so that's why we would use a paired sample, or might use one. And so what we're going to look at here and say, is there a difference between these? And we're given then our d bar, so that's the average difference between our pairs of groups, and we had 6 groups in this case, where n is 6, which gives us a degrees of freedom of 5, and then we have a calculated standard deviation for our pairs here, so of 3.5376. Okay, so those are given to us. So we need to find our t-value for the confidence interval and then the margin of error. Again, so if we just think about this though, if we've got a difference of 10 here, 10 units, whatever units these are, we don't know in this case, so we just got 10.53. What we would have to have for a confidence interval to cross 0 is a margin of error larger than 10.53, right? So we would need, so if you're going to subtract, say if it were 15, right, you'd have a negative, say, 4.47 to a positive 25.53, right? That would cross 0. And then you could say, well, there's not a difference that we can say between these two samples. Sometimes one is less and sometimes one is more, right, when you compare the two. So that's kind of, again, just sort of in essence what we're trying to do here, or what we're looking at to say, is there what is the range of possible outcomes, and if is one always larger than the other or smaller than the other, or whatever the case may be. Okay, so far so good there. So if we need then again for a confidence interval, we do point estimate plus or minus critical value times standard error. It's the standard way of doing that, or the simplified way for any confidence interval estimate, and how you calculate those values depends on the characteristics of the problem you've got. So our point estimate here is the d bar, so and that's this formula right down here. Point estimate d bar plus or minus our critical value t times our standard error, which we take the standard deviation that we calculated and divide by the square root of n. Okay, and in this case being 6. So we've got most of the things, or actually we've got almost all of the things we need, but first we need to get our critical value t for a 90% confidence interval estimate, so we can get it off of the table here. So we look in the confidence level row, and then we find so 0.9 for our 90% confidence interval estimate, and then we find our degrees of freedom 5, and so our t, the critical value, is going to be 2.0150. Okay, so then we have, if we were just write this down, then our formula, we have 10.53 plus or minus 2.015 times 3.5376 over the square root of 6. Okay, so now let's look at the margin of error. That's what we need now, and that's all this to the right there, the plus or minus. Okay, so that's what we're going to add and subtract from our 10.53. All right, so we've got, so let's take this one at a time. So if we just look at this here, we've got about 2 in our critical value, and then we have 3.5 divided by, let's say, if the square root of 6 is about 2.5 or so. So we're going to have about plus or minus 3, I would say, and we'll look at this in a second. But that should give us an idea here, you know, of what we're looking at here. So, you know, earlier I talked about how large our margin of error would need to be to say that there's no difference between these two, and we probably will not approach that. Just kind of, you know, it's always a good idea to kind of look at the numbers and say, well, what is that? What do we think that's going to come out to be? About what should that be? So that just kind of a common sense test of a result. So if you get something crazy, you're kind of going, does that make sense with what I just wrote down on the page, right? So again, about 2 times 1.5 or so. We should get a plus or minus 3, give or take. Okay, so if we look at this now, we'll just do the plus or minus 2.015, and then if we divide 3.5376 by the square root of 6, we get 1.442. Okay, and we'll want to remember that for the next part of the hypothesis test, because this will become the denominator, this 3.5376 divided by the square root of 6. So you'll see this value repeat itself here in our next part of the problem. But then when we multiply that, we get plus or minus 2.91. Okay, so if we then add and subtract that from 10.53 for our confidence interval, we get 13.44. And then on the low end, or the lower limit, we get 7.62. Okay, and right exactly in the middle will be 10.53. So our sample result gave us a difference of 10.53, and our range of reasonable outcomes here, or range with a 90% confidence level, we can say that the true difference is somewhere between 7.62 and 13.44. And it does not cross 0, so we can say in this case that sample 1 or population 1 is going to be larger than population 2, with a 90% confidence level. All right, so from there we can then say, okay, what's the next part of our equation here? And I want you to remember a couple of things as we go forward. Remember this result here, our upper and lower limit, in particular our lower limit. And I guess I said we'll come back to this 1.442. So when we look at the next part of the hypothesis test portion of the question, what it is we're talking about here. All right, so on our paired sample, continuing on, we say conduct a hypothesis test to determine if the distribution of sample 1 is 10 units larger than sample 2. Okay, so that's a different question altogether. So I said a minute ago, remember our confidence level, our confidence interval estimate was 7.62 to 13 something, and then and our d bar again was 10.53. So all these characteristics stay the same. So in this case, we're asked this 10 units larger question, and I'll call your attention to this problem down here, or excuse me, this equation down here. So we've got our d bar minus mu of d. Okay, in that case, what we're going to say is that value normally, or many times in the problems we've done, has been 0, because we're not saying there's any difference. But here, when we get to the hypothesis statements for this problem, you'll see we have a value to put in there, which is this 10. Okay, so our hypothesis statements are going to be, the null is going to be that mu of d, or mu of the difference, is less than or equal to 10. And then the alternative is going to be that mu of difference is greater than 10. Okay, and so if we were to draw this, right, we would have a rejection region in the upper tail, and well, it says, actually this says 90% confidence interval, but alpha is 0.10, right? So that's what this should say here. Alpha is 0.10. And so what we will do then, we will get it's a one-tail test, right? If we can tell from our statements here. And the alpha is 0.1, okay? And our degrees of freedom is 5, so our critical value, or T of alpha, is going to be 1.4759, okay? 1.4759. So our decision rule then is going to be if our test stat is greater than 1.4759, reject the null, otherwise do not reject, okay? Okay, so, and again, we're just putting this picture into words with the decision rule. That's what we're going to look at, or that's what we're going to decide upon. And so in this case then, now we'll get back to this equation down here. So you remember in a moment ago in our confidence interval question, we had this denominator was calculated as part of our margin of error, and that was equal to 1.4442, I think, something like that. So this is our test statistic. So then we have d bar 10.53 minus 10. Okay, so that is this value right here, 10 units larger. So we're saying, so here's our sample result. And if we want to say that or ask or find out, can we say that it's always 10 units or more larger, then we subtract that out from our result, and we get then 0.53 over 1.4442 for our test stat. And that result is 0.3670. Okay, so you know, just from looking at this here, right, it's less than 1, right? So not to say nothing of it being less than 1.4759 standard deviations above the mean. It's just, it is above the mean, but just barely at this level, right? So we could say, or just know from looking at it, we're not going to be in the rejection region. So our answer then, because we're not in the rejection region, is that we do not reject the null. So we can say that the mean difference between the two is less than 10. Now again, thinking back to our confidence interval, the low end of the confidence interval was 7.62. So if we were to rephrase or look at this problem and say, can we say that it's always 7 units larger than sample 2? Then that would change our result, right? So instead of 10, again, this is, so we've answered the question, but just again to kind of tie them back together, can we say that it's 7 units different? Well, let's what would that be? Then that would be, t would be 10.53 minus 7 instead of 10 over the 1.4442, and that would be 3.53 over 1.442. 3.53 over 1.4442, and that's going to be greater than 2, right? So somewhere greater than 2, and which would fall into the rejection region, right? And that, so first things first, the actual problem asked, is it 10 units greater? No, it's not, and that result is consistent with the confidence interval we just calculated, which said a reasonable estimate, or a 90% confidence interval estimate for the range of possible differences was 7.62 to 13 or so. So when we ask this question in the hypothesis test, the answer we think, just at face value, should be no. Again, if we're using corresponding alpha values and confidence levels. But then, so that part of the question we know, okay, that's consistent and that holds true. But then just to kind of tie them all together, so if we did say, but what about, can we say that it's always 7 units different? The answer to that would be yes, right? And that's also consistent with our confidence interval estimate, because that 7 is less than the low end of our confidence interval. So again, just to kind of try to tie those things together and how they work together and what we could say about the results of these two samples, or what we could infer about the populations based on the results of our sample.